We left off working on some problems with 3 and 4 atom, 5 atom molecules and the different shapes that they can make. So let's look at some things that are a little more complicated. Here we have 2 different molecules. SB, anyone remember what that is? SB. It's one of the things we don't really come up with very often, but SB.
Antimony?
Yeah, it's one of those weird elements. It's a metalloid, and but yeah, it's an odd little element that does make a lot of interesting molecules. So let's look at since that's antimony or antimony, depending on what part of the world you're from. What would you call this particular compound? SBF5. What would we call that? Right, Ferris. Pentafluoride. So let's figure out how to draw it, shall we? So what group is antimony in? And hopefully everyone's got their periodic table in front of them.
Group 5.
Group 5. So how many valence electrons will it have?
Five.
Yep, it sure will. So it's going to go in the middle because it's paired with fluorine, and everything goes in the middle when paired with fluorine. And we'll put a bond between each one. So antimony has 5 valence electrons. And fluorine, we should all know by now, has how many?
7.
7. And there's no charge. We don't see a positive or negative charge. This isn't an ion. It's a molecule. So 5 times 7, 35 plus 5. So we have 40 electrons to go around. So where do we start? Where do we start putting electrons?
From outside.
Yeah, outside in. We decorate the outside. How many electrons are we going to have to decorate the outside?
30.
30, right, because we've already used 10 in making those 5 bonds, because remember, a bond is 2 electrons. So now we've only got 30 to put around. So I'll put 30 all around. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that's it. We're done. Remember, when you decorate the outside, you want to give everybody an octet. Except, of course, if it's hydrogen, because hydrogen can't handle an octet. Hydrogen only takes 2 electrons. Pretty much everybody else you're going to find around the outside needs an octet to be stable. So now we've got an octet on everybody. We have no electrons left. Now, how many total electrons does antimony or antimony have in this situation? Total electrons.
10.
It has 10, right? It has 5 bonds, 2 electrons each, so it has a total of 10. Is that cool? Is that allowed?
Yeah, because it's below the 3rd row.
Exactly. It's below the 3rd period, so it has room. It has room for more electrons than 8. So it's perfectly fine for antimony to have 10 electrons. How many valence electrons does it have in this particular model?
5.
5. So, and it usually has 5. So there's no charge. So there's no charge on antimony. There's no charge in any of the fluorines. They all have 7 valence electrons. They have the 3 lone pairs for 6, and they each have 1. Each get to keep 1 electron from that bond for a total of 8. So they have 6 lone pairs and 1 more from each bond for a total of 7. So they have 7 valence electrons. Antimony has 5 valence electrons. Everybody's fine. So now we'll use the Axe body spray model and figure out what shape is this going to be. So our central atom is antimony or antimony. How many electrons does it have around the outside?
5.
It's got 5. So we've got A, X, 5. And then how many lone pairs are on antimony?
None.
None. So it's just AX5. So then we look at our table. So it's got 5 electron groups. We look at our table. Here's our table that, of course, all of you have printed out or have in a little corner. And what shape, what orientation is that? What general shape is that?
Trigonal bipyramidal.
Yeah, trigonal bipyramidal. So basically it looks like 2 pyramids on top of each other. And so so that's the group that it's in. What's the actual shape of the molecule?
The same, the trigonal bipyramidal.
Exactly. It's the same. And it's always the same when you don't have any lone pairs. The lone pairs take what sort of group it's in and sort of make the actual shape of the molecule slightly different. Because remember, when we look at the shape of a molecule, we can't really see the lone pairs. We can see what effects the lone pairs have, but we can't really see them because they're so damn small. So in this instance, we would have the usual trigonal bipyramidal shape. So what does that look like? Looks like, whoops, looks like this. So here's our trigonal bipyramidal shape. So we would have 2 axial positions here and here. And of course, they're both fluorines. And all the positions around the outside, or the equatorial positions, they're all fluorines too. So what should the bond angles be between the axial atoms and the equatorial ones? What's this bond angle?
90 degrees.
Right. And is it 90 degrees in this particular molecule?
I think it should be.
It is, because it's everybody's the same. Everyone is the same atom. So it's completely symmetrical. So we're going to have 90 degrees between axial and equatorial. And what is the bond angle of the equatorial is going to be?
120.
It's going to be 120. It's going to be exactly the predicted. So we'll have 120 between the equatorial groups and 90 between axial and equatorial. It'll look exactly like it would be predicted because it's completely symmetrical in every way. Is everyone clear on that? Because it's symmetrical, it looks like the predicted shape. It's only when we start introducing changes, either with a lone pair or a different sized atom or something, that will like tweak the shape slightly. If it's exactly the same all the way around, it should look exactly like we would expect it to. So let's do the next one.
Professor?
So, oh, yes.
I have a question. This just might be a random thought, but do any of the elements that don't have lone pairs and that only have the, I guess I'll call it the base shape or the predictive shape, do those elements share anything in common besides them not having lone pairs?
Well, I mean, they each would have the same number of valence electrons. So yeah, I mean, they'd all be in the same group. So you would see the nitrogen pentafluoride and antimony pentafluoride and arsenic pentafluoride and phosphorus pentafluoride would all have exactly the same shape.
Oh, what I'm asking is like, does linear, trigonal planar, tetrahedral, and trigonal bipyramidal, the ones with no lone pairs, do they have anything in common, like those elements?
No, I mean they just have they have exactly the number of valence electrons that are predicted for this particular shape. Like with a molecule with four electron groups, that would be carbon. That would make four and have no lone pairs. For 5 electron groups, that would be every element in group 5. With 6, that would be every element in group 6. So it's whatever element has exactly the same number of valence electrons as electron groups. So that's how that would break down. Like boron has 3 valence electrons. So if it has 3 electron groups, it is going to be trigonal planar. It's just so that's how it would break down.
Okay, thank you.
I think that's what you're getting at. Does that sound right?
I pretty much. I was just wondering if like
How we can predict?
how we can predict, but if there was anything like chemical wise or anything that relates or something that connects these ones that don't have a lone pair. But it was just a random thought.
Yeah, no, I think it's the number of valence electrons. If the number of electron groups in that molecule is exactly the same as the number of valence electrons of the central atom, then that molecule is going to have exactly the shape that's predicted.
Okay.
Yeah, because it won't have any lone pairs by definition.
Okay.
I think that's a good way of looking at it. I've never really thought of it that way, but that's why. And actually now that's a captain segue. That takes us to the next molecule. Now we have bromine pentafluoride. Is this going to look any different? So let's put our buddy bromine in the middle and then have 1, 2, 3, 4, 5 fluorines around and go 1, 2, 3, 4, 5. All right, so how many valence electrons does bromine have? So we got bromine in the middle. So how many valence electrons does it have? What group is bromine in?
7.
7. It's remember, if it has ene at the end, it's probably a halogen. Fluorine, chlorine, bromine, iodine, they all got enes. And so they all have the same number of valence electrons, 7. So bromine's got 7, fluorine's got 7 because it's an ene too. So basically right here we've got a total of 42 electrons this time. Whereas before we had 40. So we got 2 more electrons this time. And I think you know where those electrons are going to go. So we have 42 total electrons. We've got 10 in bonds already. So that's 32 electrons. And where do we start putting our electrons? In the middle. We'll just give bromine 32 electrons and be done. Who gets the electrons? We got 32 left to put out. Who are we going to give them to? Yes, Rye. Around the outside. Everyone's quiet today. Very, very quiet. Yes, we have 32 to put around. So let's start. So remember, when we start decorating the outside, give everybody an octet. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 30. So I got 2 electrons left over. So do I put a double bond on somebody? What do I do with the extra electrons?
A lone pair around the bromine.
Right. There's a lone pair. I put them in the middle. So I put that lone pair of electrons in the middle. So let's do our Axe body spray formula. So bromine is our central atom. Why is bromine the central atom and not one of the fluorines? Why not put one of the fluorines in the middle of bromine on the outside? Why did I draw it like that?
Because fluorine's more electronegative.
Right. Fluorine's hella electronegative. It is the most electronegative. So generally fluorine, no matter who you pair it with, is just going to form that one bond because nobody else is able to pull those other electrons away from fluorine. Nothing can. So fluorine keeps those three lone pairs always. It always keeps them. And it doesn't share any electron except that one. So it's always going to form as just a single bond. So it's super electronegative. That's one reason you don't put it in the middle. And the other one is it never forms more than one bond. So that goes in, that keeps it from being in the middle as well. Excellent. Right. So bromine, also pretty electronegative, but not nearly as electronegative as fluorine. So bromine's in the middle. So that's our A. How many atoms surround the bromine?
Seven.
Got 7 atoms around it? How many atoms? Probably have this a little too.
5.
5. There you go. Yeah, it's got the 5 fluorines. So AX5. And what about E? Does it have a lone pair of electrons?
Just one.
Just the one. So it's AXE or AXEE1. Either one will do. So we can see that it has 6 electron groups around it. 5 of them are bonds. So X is 5, and one of them is a lone pair. So E is 1. So it has 6 electron groups. So we look at our 6 electron groups, and it's supposed to be octahedral. That's in the octahedral group. So we say that the group arrangement is octahedral. But what is the actual shape of this molecule going to be octahedral? Yes or no?
Professor, how is it octahedral if there's only 5?
There's 6 electron groups.
Oh, okay. Sorry. Okay.
So the overall group, the overall geometry, we say the geometry of this molecule is octahedral. There's a difference. It's difficult to find a way to talk about it where it isn't confusing. I sort of kind of look at the geometry is octahedral, but the shape may or may not be octahedral, depending on lone pairs, numbers of lone pairs and numbers of electrons. So the overall geometry of this molecule and other molecules that have 6 electron groups surrounding the central atom, that's octahedral. The shape of the individual molecule may be different. So we say that it's an octahedral geometry, but it might not be octahedral. So the geometry is octahedral. It's the shape octahedral, though.
The shape would be square pyramidal.
Right. We can immediately look at the Axe file, the Axe body spray, and we look at that and we see that E equals 1. There's a lone pair. That immediately tells us that it can't be octahedral. It's in the octahedral group. The overall geometry is octahedral, but the shape can't be because it has a lone pair in there. If it has a lone pair in there, that screws up the overall shape. It's not going to be perfectly octahedral because not every group around the central atom is going to be identical. That throws in a little bit of a change. It's not identical. They're not all completely the same. So, right, it's not going to be octahedral. We look it up. We don't have to memorize these, remember. Have your table nearby. And that's going to be square pyramidal. So what shape is that going to be? So it kind of looks, let me clear these out. It's going to look like this. So we got bromine in the middle. We've got 1, 2, 3, 4. And these are all going to be in a plane. These 4 around the middle, so these 4, those are going to be basically in a flat plane around. And then on the bottom, we've got our lone pair coming out of the bromine. So in a perfectly octahedral setup, this bond angle would be 90 degrees. Now, is this bond angle for this molecule going to be more than 90 degrees or less than 90 degrees?
Less than 90 degrees.
Why is that?
I think because the lone pair has a more electronegativity to push them up.
Yes, exactly. Well, you don't say it has more electronegativity, but it has electron density. There's electron density there, and the electron density that there doesn't have an atom at the end with a nucleus that's sort of tamping down that charge. It is just 2 electrons in space. So that really repels those other atoms. And so these 4 fluorines are going to be pushed up slightly and away from that lone pair so that this angle becomes slightly less than 90. I like how you were so sure of yourself there. Excellent. Let's have a look, see if we're right. So this is what it's kind of a weird looking shape, right? So the fluorines around the outside, these are our fluorines around the outside. And you can see that they're sort of just tiny bit pushed up. In a perfectly symmetrical molecule, they'd be all exactly 90 degrees from this one. But you can see they're just slightly pushed up by the lone pair, which would be here. And so you can see that the lone pair will make all bond angles slightly less than the ideal. So excellent job. Anyone have any questions on this one?
Will it also make the fluorines on the horizontal plane less than 90?
That's a good question. I used to actually build these sort of models for. Yes, I believe so. Because they're pushed, rather than being like this, they're sort of pushed slightly closer together. So yes, I believe all the bond angles will now be less than 90. This would be the perfect time if we were in the lab and playing with models, we could do this, and you'd actually build this with your hands and then like push them up and see what. But unfortunately, we can't do that. But yeah, I think it makes all the bond angles less than 90.
But if
So,
they're
yeah.
not pushed like side to side, only pushed up, then how could the bond angles between them change?
Because they're not on a planar. It's not planar any longer. So once you've changed that orientation, you're going to change slightly the angle. Yeah, if you don't believe me, I don't know if I believe myself, I would like make a little model and test it. But I think that they're all less than 90 now, because they're no longer on a plane. They're raised slightly, and I think that changes the bond angle.
Okay, thank you.
Because if you go all the way around in a plane, it's 360 degrees. But if it's not a plane, I think that angle changes somewhat. It doesn't add up to 360 anymore because it's not perfectly flat.
Is it because all the electron has to be like stay as far away from each other as possible?
Mm-hmm. Yeah, all the bonding regions want to be as far away from each other to avoid repulsion. And because there's more repulsion in a lone pair than in a single bond, all the single bonds will move away from the lone pair because it repels more than a lone pair does. So they'll all move away slightly. And we can measure these angles very precisely. So actually, that's a really good question. I will look up what those bond angles are and get back to you on that. Because if we had if we had two different bond angles, like this bond angle was different from this bond angle, then we should be able to measure two different bond angles. But I think they're all identical. So I will look that up for you and get back to you. I think they're all identical. Because by measuring, you can take this and actually zap it with a laser or some other strong light, and see how the different these different bonds vibrate. And if they all vibrate at the same frequency, then they all have the same angle. And I think they all vibrate at the same frequency. So I will check that for you. That's a really good question. And unfortunately, I don't have, my male brain is supposed to be able to see things in 3D in my head, but I can't do that very well. I'm really bad at it. However, my wife is really good at it. So what do you know? So I've had some questions about what if the molecule has more than one central atom. So here's two molecules that have basically two central atoms. One, ethane on the left, that has a carbon here and a carbon there. And you can see that they're basically in the identical situation. They each carbon is bound to another carbon and 3 hydrogens. So they're each AX4. So they're each tetrahedral. This one is tetrahedral, and this one is tetrahedral. I want you to look at this a little more closely. And does anyone see what's going on with the hydrogens in that molecule? It's drawn that way for a reason. Anyone see how the hydrogen atoms are drawn? Do you notice anything about it? Are they in the same orientation on both carbons? They're mirroring each other. Are they, Rye, though? I would say they're not. They are not mirror images of each other.
They're like upside down mirrors. I don't know.
Yeah, they're upside down. Exactly. On one, if you turned it so that the two carbons were right behind each other, you would notice that on carbon 1, the hydrogens look like this, right? 1 on the top and 2 on the bottom. If we look at carbon 2, the hydrogens look like this, 2 on the top and 1 on the bottom. And that is because if they were to be exact mirror images of each other, all of those atoms would be closer together. And we would say, when you take organic chemistry, we will say that they would be eclipsed. So if they all lined up perfectly, they would come into closer contact with each other. And even though that's a very weak interaction, that is some repulsion. There's some repulsion there. And so they move. So you have, instead of them being directly across from each other, they sort of move out of the way to make a little more distance between them. And so we say that they're not eclipsed anymore. Same is true with ethanol. So this is ethanol on the other side. Ethanol is just ethane with this OH group, oxygen and hydrogen. We call that an alcohol group or a hydroxy group. It's got O and H at the end of it. So we can see the same thing is true here. Each carbon has 4 bonding groups around it. One of them is the carbon, and carbon 1 has 3 hydrogens around it, so it's AX4, it's tetrahedral. And carbon 2 has 2 hydrogens and an oxygen bound to it, as well as the carbon. It's also AX4. It's also tetrahedral. So in each of these instances, you'd say that both carbons are in tetrahedral arrangements, as well as the oxygen. The oxygen's tetrahedral as well, because it also has 4 groups, right? So it has 2 bonds and 2 lone pairs. So it's in the tetrahedral group, but it is what shape? That would be AX2E2 for the oxygen. What shape would we say it has? It's in the tetrahedral family. It's not a tetrahedral shape.
It's a bent shape.
It's bent, right? Just like water, it's bent. Because remember, we can't see these lone pairs, but we can see the effect they have. So whenever you have oxygen with 2 bonds, it's always going to look like it's bent.
Professor?
Yes.
If we draw our molecules as eclipsed, will we get points taken off?
No, I just want to introduce that to you because that's something that comes up in organic. And I just want you thinking about when molecules take their particular shapes, they basically do everything possible to minimize repulsions. Because the whole reason for forming molecules is to reduce energy. You want to get the most stable molecule you can. It's the whole driving force. When we talk about thermodynamics a little bit later, the whole driving force for all these reactions and everything is to get to a lower energy. It's the whole point of doing it. So you go from a place of high energy to a place of lower energy. Well, this is one of the ways you lower that energy, by moving things around until all the electron repulsions are reduced as much as humanly possible. And then anytime something from the outside changes it, you're changing that energy. You're making it a higher energy. You're causing instability. And that's what makes, so someone had asked me questions about explosives before. That's what causes instability. If you have a molecule that's unstable because its shape causes a lot of repulsions, that's potentially explosive, because that molecule is in a higher energy. And so when it comes apart, then it lowers its energy. So explosives generally tend to be molecules with a lot of repulsions in them that are very unstable. And basically all it takes is someone just like tapping them or a match or something, and they fly apart because they're unstable and want to achieve stability.
Professor, I hope this is not too off subject. So what's like rocket fuel then? Like what's like used?
There's a lot of different rocket fuels. You can look up hydrazine. Hydrazine was one of the earliest rocket fuels. Basically, what you want in a rocket fuel is something that contains a lot of nitrogens. I think hydrazine is this. I can't remember. Anyway, something that when you burn it, it creates a lot of stable gas. So something that releases a lot of nitrogen and hydrogen gas, and then the hydrogen could be burnt and to release water on top of that. So basically anything that has a lot of nitrogens in it is good, because nitrogen really likes to be triple bonded. And so if it's single bonded with a lot of other elements, it's much more stable when you break those bonds and form nitrogen gas.
So it's not the instability that's giving something energy or propulsion or something, like
it's the production of stable molecules, and the more gases you can make, the better, because it's the exit of those gases that causes it to be propelled. So the more gas you can make, the better.
Okay, thank you.
Yeah, because one of the earliest rocket fuels was kerosene. We don't think of kerosene as being particularly explosive, but it releases a lot of gas when you burn it. You just have to burn it very, very quickly. So here's an example of molecule that's going to have more than one central atom. And this, again, we're going to learn a little organic chemistry. This is acetone, or nail polish remover. And it has this particular, oops, let me go back. It has this formula right here. CH3, so it's got two what we call methyl groups. And it has a central, what we call a carbonyl group, which is a C double bond O. So what I'll do is I'll draw this for you, and then we see if we can predict what the shapes around each of the carbons is going to be. So, as I mentioned, it's going to look like this. So we have a, oops, damn it. There we go. So we have a central C double bond O, and in organic chemistry we call this a carbonyl. Don't have to remember that. And on one side we have a methyl group, which is 1, 2, 3. It's just methane, but instead of another hydrogen, it has a carbon-carbon bond. So we call it methyl. And on the other side we have the same thing. 1, 2, 3. H, H, H. So I've got 3 carbons. I got carbon A, carbon B, and carbon C. So let's do X for each one. Oh, and our oxygen has 2 lone pairs. There's 2 bonds and 2 lone pairs, which oxygen 98% of the time is going to have. So for carbon A, what is my AXE going to be? How many electron groups are around that carbon? How many atoms surround carbon A? So here's my carbon A. How many atoms surround carbon A?
4.
4, right. So I have A, X, 4. How many lone pairs?
0.
None. So I've got AX4. So what group, what overall geometry is AX4?
Tetrahedron.
Mm-hmm. And so what shape is it going to be? Remember, there's no lone pairs. And if there's no lone pairs, the shape and the geometry should be the same. So if the overall geometry is tetrahedral, what's the shape going to be? Yes, Pavlin. It's going to be tetrahedral as well. So this A is going to be tetrahedral, and we saw that with the methanol and with the ethane, ethanol and ethane. Each of the carbons had 4 atoms around it, and they were both tetrahedral. So A is going to be tetrahedral, and that means C is going to be tetrahedral as well, because they're exactly the same. Each one of them is a carbon with 3 hydrogens and a carbon bound to it. They're both AX4. They're both going to be tetrahedral. What about carbon B? So carbon B in this instance is our central atom. How many atoms does it have surrounding carbon B? You want to tell us that, Mavlon, or?
Yeah, I would say 3.
3, right? It has 3. It has this carbon, and this oxygen. Those are the 3 atoms surrounding carbon B. So it's AX3. Does it have any lone pairs carbon be?
No.
No. So it's just AX3. So what group is AX3? What geometric group is that? If you're an atom, 3 groups surrounding you. Right, Nick. It's trigonal planar. Right. The lowest energy, the most stable form that you can form when there's 3 things surrounding you is to keep them on a plane at 120 degrees. That keeps them as far away from each other as you possibly can get. And so that is trigonal planar. This carbon is trigonal planar. So one last question. I just told you that within a trigonal planar molecule, these angles, let me erase some of this stuff because it's a little confusing. So the angles between these different atoms when it's trigonal planar is 120. So this and this should be 120 degrees. In this particular molecule, is this angle going to be more than 120 degrees or less than 120 degrees? Remember the things that keep it from being ideal. If there's not equal electron density all the way around, it's not going to be ideal. It's going to change. Now, if you look around the carbon, does one of those electron groups have a higher density of electrons?
It's going to be more because there's a double bond.
Exactly. Excellent. Yes, that is true. Remember, a double bond is nothing more than twice as much density of electrons in space. That's all it is. It's just more electrons in that space than here. So this would have a lower density, this would have a lower density, and this would be twice as much. So since there's twice as much electron density, it pushes those two CH3 groups slightly further away from it. So this angle will be slightly more than 120 degrees, and this angle here will therefore be slightly less, because they all have to add up to 360. So if this angle is greater and this angle is greater than 120, then this one has to be slightly less. So let's see if we are right. So here's what it looks like. And we were correct that we have a trigonal planar overall shape because this carbon is trigonal planar. This is tetrahedral on one side, this is tetrahedral on the other side, and you're also right that this bond angle between the oxygen, the carbon, and this other carbon is going to be slightly more than 120 degrees, 122. So slightly more, because there's more electron density in that double bond, and it pushes the other groups slightly further away from it. So excellent. We did well on that one. So,
Right.
yes.
What would xenon trichloride look like?
Xenon trichloride. Xenon trichloride. Why don't I send me an email about it? And because it's a great question. I want to get caught up though. So send me an email and we'll go over it. Is that okay?
All right.
Yeah, because I kind of want to get to hybridization if at all possible, because that's what our recitation is going to be about today. So I'm sort of, but yeah, it's a really good question. I don't even know if it's possible to make it because I don't know. I guess probably it might be. Okay, so this is something we sort of dealt with already. We sort of looked at it a little bit, talking about now that we know what the shapes are and we know what the polarities of bonds is, it means a difference in electronegativity. Basically, it means that in a bond, which is just, remember, that is just the density of electrons. Now, if X is more electronegative than Y, it pulls that density towards X and away from Y. And so we have slightly more electron density here than we do there. And then we draw an arrow like that showing which side is slightly positive and which side is slightly negative. So the Y would be slightly positive because there's slightly less electron density there. And X is slightly negative because there's more electron density there. So that's a polar bond. But that doesn't tell us whether or not the overall molecule is polar, because if it's completely symmetrical, the individual bond dipoles cancel out. It's completely symmetrical. We add them all together and they basically come up to 0. Now, what is just adorable about this is that the polarity of a molecule is measured in Debbies. It's just so cute. How many Debbies is it? You know, it's such a Debbie. So we get a polar molecule if it has you need to have polar bonds, and if they don't cancel out. And so we've looked at this already. I haven't mentioned Debbies before, but it's just so damn cute. And this was one of the things we did in our virtual lab, determining whether or not a molecule was polar, is if it is polar and you put it in an electric field, it should orient itself in the electric field. So on one side, we have an anode, and one side we have a cathode. We have opposite charges. And then our molecule will automatically orient itself so that the slightly positive side points to the negative pole, and the slightly negative side points, or slightly positive side points to the negative, slightly negative points to the positive, and it orients itself. If it's a nonpolar molecule, it won't make any difference. Remember, we turned on if we have a nonpolar molecule, it's basically just like a hydrocarbon, and you turn on the electricity, it doesn't orient, it just keeps floating around randomly. It will not orient itself in space. But something like HF here has a definite slightly positive side and a slightly negative side because of the fluorine. It will orient itself in an electric field. That has just one dipole. It's easy to see whether or not it's going to be polar or not. It just has one dipole and it's polar, the end. What if it has more than one bond dipole in it? And we've already looked at this. You know, this is a classic example of a molecule that has more than one bond dipole in it because there's two bonds, and so two bonding groups, I should say. So it has two bonding groups, and so it's a dipole in this direction, and it's a dipole in this direction. And remember what I said before about these are like vectors. And if you've taken physics before, even if you haven't, don't worry about it. But basically a vector is something that has both an amount and a direction. So it has two things. So the amount in this instance is this difference. That tells you how polar it is. And the amount of each of those dipoles is exactly the same because we have the difference between carbon and oxygen. Carbon is an electronegativity of 2.5, oxygen's 3.5. So the dipole goes in that direction. But on the opposite side of the carbon is another oxygen. And that difference is exactly the same. And so those dipoles are exactly the same size. Now, once we have the dipoles at exactly the same size, now we have to look at the direction. And if they each go in the same direction, then they add up, either up, or if they're bent down, the dipole will go down. But the net dipole is adding up both the direction and the total amount. And you can see here that the directions are completely opposite. This is a completely linear molecule, meaning that these dipoles are exactly pointing in opposite directions. That is symmetric. They're pointing in exactly opposite directions. If they're pointing in the same direction, we would add them up. But since they're pointing in opposite directions, we cancel them out. And so the molecule, we say, has no net dipole moment. Each bond has a dipole moment, yes, but the molecule itself does not, because they cancel each other out. Anybody have any questions about how do we know whether to cancel them out or add them together? Is that clear to everybody? Why we do that? Remember, if it's symmetric, that's the real key to all of this. If we have a completely symmetrical molecule, it really doesn't matter what the bond dipoles are, because it's completely symmetrical. All the bond dipoles, when we add them together, will cancel if they're all completely symmetrical. So hopefully that's apparent. Let's look at so water. We've looked at this before. Now this introduces, we have two equal dipoles in water as well. So the strength of the dipole, let me go back. The strength of the dipole is always the difference in electronegativity. That tells you how big that arrow is going to be. And again, we have two bond dipoles. We have one between hydrogen 1 and the oxygen, and hydrogen 2 and the oxygen. And they're each going to be exactly the same difference, 3.5 minus 2.1. That's how long we make the dipole. But look at it, when we look at the shape down here, we can see that those dipoles do not cancel each other. They're not pointing in exactly the opposite directions. This isn't a completely symmetrical molecule. You can see that it's different on the top and on the bottom. It's not completely symmetrical. It's symmetrical in one plane. If we look at it straight down, it's symmetrical that way. But if we look at it through this particular axis, it's not symmetrical. A completely symmetrical molecule has to be symmetrical no matter which way you look at it. Water doesn't count. So we have these two bond dipoles, both pointing towards the oxygen. So when we add those two together, we get an even larger dipole pointing up. This is our net. That is our net molecular dipole, is adding all the bond dipoles together. And it has a large net dipole pointing towards the oxygen. And remember, when we made these structures in our lab, and I looked at the distribution of electrons, we saw like this, where there is definitely slightly negative charge. There is more electron density on top of the water than there is on the bottom. That makes it polar, makes it very polar, as a matter of fact. Water is one of the most polar molecules there is. And so that's why water has two equally sized dipoles. Carbon dioxide has two equally sized dipoles, but one of them is polar and one of them isn't, all because of the angle those dipoles make. Okay, any questions about that?
Professor, how do you know which direction the arrows point?
Oh, great, perfect question. Are they pointing in the same direction or opposite directions? So if they're both pointing in the same direction, we would add them together. And notice that each of these are pointing up. I mean, they're not pointing straight up, but they're both pointing at the oxygen. So if they're both pointing at the oxygen, then when we add them together, we'll get a bond, a molecular dipole pointing towards the oxygen. That's a great question.
Like,
Yeah,
how can you
that's
tell the
how we know.
hydrogens are going to point at the? How can you tell the hydrogens will point at the oxygen?
Because hydrogen has less electronegativity than oxygen. So when we remember that what this dipole means is we have a slightly positive side and the arrow points to the slightly negative side. And since hydrogen has a lower electronegativity than oxygen, if we look at this bond as just the density of electrons, the oxygen pulls those electrons toward itself and away from the hydrogen. So we have a lot more electron density near the oxygen, making it slightly negative and the hydrogen slightly positive. And then when we draw the bond dipole, it would go in that direction. So each of those bond dipoles points away from the hydrogen and towards the oxygen. And since they're each pointing towards the oxygen, when we add them together, the whole thing, the net dipole, points towards the oxygen too. And that's what makes it a polar molecule. Is that cool?
Yes.
All right, awesome. So this next molecule gets us into symmetry. Remember, I've talked a lot about symmetry. Nature loves symmetry. It will put things into really weird shapes as long as they're symmetrical, because things that are symmetrical are stable. You have something that's completely symmetrical. Basically what that means is you've moved away all the atoms basically as far away from each other as they can possibly be, because it's symmetrical all the way around. All those bond angles and all those atomic distances are all the same. And so if it's symmetrical, it is going to be stable. So here we have a molecule that we used to call carbon tetrachloride. This used to be actually back in the 70s and 80s, maybe well before then. This was used in dry cleaning until we found out that it's super toxic and just destroys the ozone layer in a pretty big way. So it's been phased out. You can't even. I was watching a YouTube video of some poor organic chemist. He said he can't even find it anymore. So you can't even purchase it. It's so toxic. But it has 4 really polar molecules, because chlorine is way more electronegative than carbon. So it has 4 bond dipoles, but they're all pointing towards the chlorines, and none of them are pointing towards the carbons. And it's completely symmetrical. And as I mentioned, if you have a molecule that's completely symmetrical, all those bond dipoles are going to cancel each other out, because they're all pointing either in the same, they're all pointing in opposite directions, or in the same direction in exactly the same orientation. They're going to cancel each other out. And so this has 4 polar bonds and no net dipole. So the net dipole is 0. But all you need to do is just make one substitution, change one of those chlorines to a hydrogen. Now we have 3 dipoles pointing away from the carbon, and one of them pointing towards the carbon. Carbon has slightly more electronegativity than hydrogen does. And so it pulls electrons away from the hydrogen. So now we have one little dipole pointing towards the carbon and the other 4 pointing away from it. Well, now when we add them all together, they're all pointing down. Now it's polar. And it has a little over 1 Debbie's. Now it's polar because it's no longer symmetrical. And so we can't cancel all the bond dipoles. Okay. So is that clear to everybody? You just change one thing, and I think this was one of the molecules we used in the lab. We looked at carbon with 4. I think it was with fluorines. 4 fluorines, 3 fluorines, 2 fluorines, 1 fluorine, and saw that when you change the orientations, you take something that's nonpolar and you make it polar. Okay. So I just want to do one of these questions So ammonia we've done before. Ammonia we've seen is polar because it has this lone pair at the top and hydrogens at the bottom. And so all of the bond dipoles are pointing at nitrogen and up. And so this has more electron density on the top and less on the bottom. So ammonia is super, super polar. Just like if we look at boron trifluoride, which I don't know why it's, here we go. We have three dipoles, three bond dipoles, all pointing away from boron in the same 120-degree angles. So since they're pointing in basically completely opposite directions, they cancel each other out. And so this molecule would be nonpolar. But the one I want to sort of go over with you in a little more detail is this molecule, carbonyl sulfide. Now this is SCO. So let's just draw this real quickly. So how many total valence electrons do we have for S, C, and O? Sulfur, carbon, and oxygen. How many does sulfur have?
16.
Whoa. So how'd you get, you're right. So yeah, sulfur is 6, oxygen is 6. They're both in the same group, 6. Carbon is 4. So yes, total is 16. So we go 1, 2. That leaves us with 12. And then we decorate the outside. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. But do we have an issue here? Let's count the total electrons. Sulfur has 8, right? It has its 3 lone pairs and a bond, so it has an octet. Oxygen is an octet because it has its 3 lone pairs and a pair in the bonds. But carbon, poor little carbon, how many total electrons does carbon have? Total now. Does it have an octet? What do you think? Octet for carbon or no? No. Everyone just wants to type in the text. Yes, it does not have an octet. It's got one, oops. It has 1, 2, 3, 4 electrons, all in bonds, and that's it. Doesn't have any more. So what are we going to do to give carbon an octet? Two extra nons. No, I don't know if nons are going to get the job done. They're delicious, but there you go. 2 extra nons, man, that sounds pretty good right now. Yes, we will move this pair of electrons to the middle, and oxygen will donate this pair of electrons over here, and so we'll wind up with this. 1, 2, 3, 4, 1, 2, 3, 4. Now everybody has an octet. Everybody's happy. The question is this a polar molecule or a nonpolar molecule? Now, what's the difference in electronegativity between sulfur and carbon? Anyone have their electronegativity tables in front of them? Is that a polar bond? Is a sulfur-carbon bond polar?
No.
No, their electronegativities are practically the same, right? I think they're both 2.5. So we don't have a dipole here. So here, there's no dipole. What about the difference between carbon and oxygen? Is that a dipole? A bond dipole? electronegativity of carbon, 2.5. Electronegativity of oxygen, 3.5. Is that a polar bond? So is that a polar bond? And if it is, what direction does the arrow point? Two questions. Is it a polar bond? C. Yes, Ahmed, man, you are on it today. Yes, it is a polar bond, and it points towards the oxygen. So if there's no dipole here, and there is a dipole there, do I have a polar bond or not? I mean, this is a linear molecule. Is it, it's not symmetrical though. Is it a polar molecule? When I add up all the dipoles, remember you have to add all the dipoles of the molecule together to see whether it has a net molecular dipole. Does this have a net dipole? What do we think? Yeah, exactly, Nang. It is. It is polar. Because the electron density is being pulled towards the oxygen. So we have two double bonds, yes, but the net electron density is going to be higher on this side than on this side, because oxygen is more polar than sulfur. It's going to be pulling those electrons away from carbon more than sulfur is. And so we have slightly more electron density on one side than we do on the other. We have a slightly negative side and a slightly positive side, and it is polar. So one more thing I wanted to show you. These are some of the effects that polarity can have. So this is ethene, dichloroethene. Ethene is the same as ethane, but with a double bond. So we have carbon-carbon double bond with hydrogens. We would call that ethene. But here we have two chlorines. So we call it dichloroethene. And notice there's two different ways you can draw that same molecule. Now, one of the things we learned that when each of these carbons has three groups around it. So what are they? Trigonal planar. And one thing we haven't learned, but we will, is that when you have a double bond like this, basically you're locked. It doesn't rotate. When we have single bonds, they can rotate around. When you have a double bond, basically they're locked into place. They can't move. And so in this instance, we have two chlorines that are on the one side of the double bond and can't move. And on the other one, we have two chlorines on the opposite side of the double bond and can't move. And in organic chemistry, we call this cis or same. They're on the same side. And we call this arrangement trans or opposite sides. So here the chlorines are cis. They're closer together. And on the other side, they're on opposite. They're further apart. And so look at the dipoles they make. Here on the cis side, both dipoles are pointing away from the carbons. That makes it polar. Because when we add up those two bond dipoles, it points down. Now let's look at the trans. We have one dipole going in that direction, the other dipole going in that direction, completely opposite directions, and they're exactly the same size. No net dipole. So even though it's exactly the same molecule, one form of it is polar and the other is not. And you can actually physically separate those those two, even though they're the same molecule, you can separate them by boiling them, because one will have a lower boiling point. This will have a lower boiling point because it's non-polar. This is polar and will have a slightly higher boiling point. Any questions about that? How one can be, it's the same molecule, yet it can both be polar or non-polar depending how you arrange the atoms? I mean, we'll see this again. And when we talk, actually what we're going to be talking about next is how these double bonds are made, how these single bonds and double bonds are actually made in space. So when you see how the double bond is made, you'll see how it basically locks that orientation in, and you can no longer move. I mean, just think of it this way. When we put two fingers together like this, you can twist them. When you put two together, you can't, right? You can't just twist them. They have to keep together. You can't twist them anymore. Your thumbs now stay on the same side either way. So that's the way that sort of bonds work as well. So I want to these are just some of the changes. So we see a change in electronegativity introduces bond polarity. Now, depending on the shape, that may introduce molecular polarity. We have polar molecules, non-polar molecules. And later we'll learn that the polarity of molecules changes the forces between them. Polar molecules attract each other. And that makes sense because they have slightly positive and slightly negative sides. We know that water molecules attract each other because they have slightly positive and slightly negative sides. The slightly positive interacts with the slightly negative. That changes their physical properties. That's why water boils at such a high temperature, and something like gasoline with a low that's completely nonpolar boils at a much lower temperature. It changes the solubility of things. Polar, water, oil don't mix. Why? Because water is polar and oil is not. And it also changes their reactivity. The shape of molecules, things that have like I mentioned before, have a very strained shape with a lot of atoms or electron groups and very close to each other, will be super reactive. And molecules that are very, very symmetrical will not. They'll generally not very reactive because they're very, very stable. So I just really quickly, as the last few minutes, want to introduce orbitals and orbital overlap. And obviously we'll talk more about it in the recitation this afternoon as well as the next class. So it starts the next chapter, and we'll learn really how things bond. We know that there's polar bonds, and there's non-polar bonds, and there's ionic bonds. Okay, great, got it. But how do they actually form? Because basically we've been taught two different things that don't equal each other. And I'll show you what I mean. So we'll learn first about the valence bond theory. This is sort of the basic understanding of how those atomic orbitals we learned about, the s, p, d, and f orbitals, how we use those and basically hybridize them together. We add them together to show what molecules actually do. And that's what the orbital hybridization is. And then we'll look at how these orbitals overlap each other. And a bond is just basically when orbitals overlap each other. And we put electrons in the same region of space. And that will give us different types of covalent bonds: single bonds, double bonds, triple bonds. And then later on, and I'm not going to spend a whole lot of time on it because we'll talk about a different theory of bonding. It's a very, very recent theory called the molecular orbital theory, which explains some things that this valence bond theory does not. But I'm not going to spend a lot of time on it, just a little bit to explain some anomalies. So very, very basically, valence bond theory just says that you make a covalent bond when the orbitals of two different atoms overlap each other. Well, that makes sense, because if you have an orbital containing an electron here, and you have another orbital containing an electron here, and they come together in the same space, well, now you got two electrons in the same space. That makes a bond, right? So the space formed by these two overlapping orbitals accommodate two electrons, just like the atomic orbitals did. You remember each box that we made, we could put a maximum of 2 electrons in each one. Each one was an orbital. And so, yeah, maximum of 2 electrons. Cool. And they have opposite spins. Yeah, got it. Just like an atomic orbital would. That makes sense. And the greater the overlap, the more they overlap, that stronger that bond would be. So if they overlap completely, that makes a really strong bond. If they overlap a little, it would be slightly weaker. And so the extent of how much they overlap depends on what kind of orbital it is, what kind of shape is it? Is it an S, is it a P, is it a D? And what directions they are. Do they completely are going in the same direction? Are they in slightly different directions? Both of those things would make it either stronger or weaker. So I'll give you an example. So the simplest example is just hydrogen, H2. So remember, one hydrogen has an electron and it's 1s pointing up. The other hydrogen has a single electron and it's 1s pointing up. When they overlap each other, you get this overlap right here. That's where they overlap. And now we have 2 electrons in that overlapping region. One of them flips. So now we have one spinning up, one spinning down, and this is a covalent bond from a 1s coming in contact with another 1s. And so we have more electron density between them. That makes a bond. Everything's cool. Okay? So far, so good, right? It gets a little more complicated when we have different orbitals overlapping each other. So here we have hydrogen fluoride. So our hydrogen, good old hydrogen, still has its 1s pointing up. But if you remember, fluorine has its bonding electrons in p orbitals. Remember, it's in 2p. It had 1, 2, 3, 4, 5, and missing 1 electron in 2pz, this last orbital. That's where its one available bonding electron is. And so there it is, right there. And it overlaps. Notice that it doesn't overlap completely because the shape of the P and the S are different. S has a round spherical shape and P has that sort of more narrow balloon animal shape. So they do overlap, but they don't overlap quite as much. So the bond is slightly weaker than it would be if you have a complete overlap. Like if you have 2 fluorines coming together, note that this overlap is much better. That's almost complete overlap. So this bond is going to be stronger than this one because the 2 P's overlap each other almost perfectly, and S and P not quite. So it's going to be slightly stronger bond. So what we say is the orbitals that form when these two things overlap each other are going to look slightly different than the atomic orbitals are going to look. Because they're basically going to merge their shapes. That's what's going to happen. Their shapes are going to basically merge together. If I have an S and a P merging together, it's going to be a slightly different shape than either an S or a P would be by themselves. They're going to be slightly different because if no change occurred, we could not account for any of these molecular shapes that we've been talking about. And I know I'm going a little over. I just want to go a little over today to introduce this. So atomic orbitals mix, or they hybridize. We mix them together. So if we mix an S and a P together, they have some of the properties of an S and some of the properties of a P. And the spatial orientation of these hybrid orbitals, these new mixed orbitals, correspond with the shapes we've seen. Now, I just want to briefly show you what I'm talking about. And I'm going to introduce the problem with methane. Oh my God, there's a problem with methane. Now, let's look at the electrons for carbon, right? It has how many total electrons? Carbon. So here I've got my 1s, my 2s, and my 2p. So how many total electrons does carbon have? 6, right, Nick? And so I go 1, 2, 3, 4, 5, 6. So these are my valence electrons, right? These are my outer shell electrons that are in carbon. Now, I have 4 electrons. And notice, I've got 2 that are in 2p, and I got 2 that are in 2s. Now, the 2p, you remember what shapes those were? Those were like this. And they were 90 degrees apart. Remember, we had 3 different ones. We had one going in and out. That was the shape of the p orbitals, right? And they still are. That's still the shape of the p orbitals. They're 90 degrees different. And s, they're in a sphere. But when I make methane, all 4 of those bonds are the same. They're exactly the same. And they're separated by 109.5 degrees. That doesn't mix with these 4 electrons, because these 2 in the p orbitals are at 90 degree angles to each other. And the other 2 are in a sphere. None of them are at 109.5 degrees. So these cannot be the 4 bonding electrons for methane. Can't, because that doesn't make any physical sense. We don't have electrons in methane in that orientation. We just don't. We know we don't, because we've measured these bond angles. They're all the same. They're all identical. You have to have 4 identical bonding electrons to make methane. And here, we don't. And so that is what came up. That's what had scientists coming up with the idea that something's got to be different between how electrons are organized in an atom and how electrons are arranged in a molecule. Okay? And we'll get to how that is next class. So any quick questions about this so far? I just sort of introduced the problem, and then next class we're going to deal with how to solve it.
I don't really understand the problem.
Oh, the problem is I have my carbon has 4 bonding electrons. 2 of them are in this sphere in the s orbital. So 2 of them are here, and 2 of them are here at 90 degree angles from each other. That's not what a methane molecule looks like. Methane molecules have 4 bonds, each at 109.5 degrees from each other. These 4 molecules in carbon are valence electrons in carbon do not have that orientation. So when they make a methane molecule, they have to change their orientation. They just have to, because they're not in this we don't have a 90 degree, we don't have 2 bonds with a 90 degree angle between each other and another 2 just sort of in a sphere. We don't have that. They're all exactly the same. They're all exactly 109.5 degrees from each other. So this orientation of our valence electrons is impossible. It cannot be that way. We'll talk more about it the next class. But yeah, we don't, all the angles and everything in the atomic orbitals do not match the molecule. So they can't be the same. Does that make a little more sense?
Yes.
Yeah, it's the 90-degree angles of the p orbitals that screw everything up, because they're not 90 degrees. So they can't be in just p orbitals. They have to be in something different. And we'll see what that something different is next time. Okay? Okay, so get out and vote if you haven't today. And don't freak out regardless of, remember, the election will not be over tonight. It probably won't be over till January. We wished it would be over, but we'll see. Anyways, stay strong, stay safe, and Mitra groups, I will see you this afternoon. I posted the recitation. Obviously, I'll go over more of this before we get started on it, and we'll deal more with this on Thursday, okay? So I will see my groups this afternoon. The rest of you, I will see you on Thursday. I have office hours tomorrow. Drop in if you have any questions about this or your test or anything else, just to say hi or, like, you know, have a cry with, whatever you need to do. I'll see you tomorrow. All right. Have a good day, everybody.